Hi, I'm William from the University of Chicago Reproducibility Journal Club, and I'm recording in this video my presentation on questionable research practices. It's based around the Simmons, Nelson, and Simonsohn 2011 paper, False Positive Psychology, Undisclosed Flexibility in Data Collection and Analysis Allows Presenting Anything as Significant. So what is the context? So hopefully in this video, by discussing this paper, we'll find out what are questionable research practices and how easy it is to accumulate statistically significant evidence for a false hypothesis. Okay, so what is a false positive in the first place? So a false positive is the incorrect rejection of a null hypothesis. So you find a significant effect when there is none. And scientists should really care about false positives because they can be persistent in the literature, typically because failures to replicate and null results are not commonly published in journals. Journals like to publish a significant effect rather than not finding an effect. And false positives can lead to a waste of resources, especially from investment in fruitless research programs. So for example, if you try and replicate a false positive and you are unable to in the lab, you've invested all the resources that you've done to run the experiment in the search of not finding the effect. And these false positives in the literature, because they persist, can be used to justify ineffective policies or ineffective government policies. So the author suggested it is easy to publish statistically significant evidence, so to publish significant results from false positives, due to researcher degrees of freedom. So what are researcher degrees of freedom? It's when a researcher makes decisions on things like, should more data be collected? Should certain observations be excluded from the data? And which variables are included in the analysis? So which dependent variable might be analyzed or combined. Another word in the literature for researcher degrees of freedom that I've seen is also analytical flexibility. So the decisions that are made when collecting or analyzing the data may lead to an increase in false positives, according to the authors. And so let's see how they demonstrate this. So the authors of the paper, Simmons et al., set out and collected real data. They got 30 undergraduates and they were randomly assigned to Kalimba or Hot Potato, a song by the Wiggles. And after that, they were asked, how old do you feel right now, using a 5-point Likert scale. So in ANCOVA, analysis of covariance, revealed people felt older after listening to Hot Potato compared to Kalimba. So you can see there the F value is 5.06, and the P value was 0.033, which is less than 0.05, so it's a significant result. So this is seemingly evidence that listening to a children's song makes people feel older. But does listening to a song about older age make people actually younger? Let's see. So in the second experiment they ran, the cheekily titled Musical Contrast and Chronological Rejuvenation, the authors, Simmons et al., got 20 undergraduates to listen to either When I'm 64 by the Beatles or Kalimba, the same control condition from the first experiment. They then indicated their birth date and their father's age. So the father's age was used as a covariate in the analysis, in the subsequent analysis. And then ANCOVA revealed people were nearly a year and a half younger after listening to When I'm 64 rather than to Kalimba. The F statistic there is 4.92 and the P value is 0.040, which is less than 0.05, so a significant effect. So it appears that we have evidence that people were younger after listening to a song about older age. So clearly this is false. People do not get younger after listening to music. But here you can see a scenario where we seemingly have evidence that it is the case. So what do these studies demonstrate? Well, using real participants, real data, and legitimate statistical analyses, hypotheses that are false, right, the ability to become younger after listening to music, were seemingly supported. So some people might be, after seeing those results, might be, yeah, okay, this doesn't happen very often. So how often can this happen? Was this just a one-off? So the authors took the next step and ran some simulations. So how bad can it be, simulations? So what they did was they generated 15,000 samples and with at least one significant result, where they had certain scenarios. So situation A here was t-tests on either of two variables or the average. So they collected two dependent variables, so you could run your statistical tests on either variable, A or B, or a combination of the two, like an average. So you can run a t-test on A plus B. Situation B, which is adding 10 observations to each cell of not significant. So they simulated 20 observations per cell here. If the result was not significant, they added an additional 10 observations to see, and then reran the statistical analysis test to see if they were significant. Situation C is adding gender as a covariate so like using an ANCOVA rather than an ANOVA. And situation D, which is dropping conditions. So if you had a low, medium, and high manipulation, you might drop the medium manipulation, for example, to only analyze the low versus high conditions. They also examined doing a combination of these four things. And you can see here in the table the likelihood of obtaining a false positive result. If you take two dependent variables, they're correlated by 0.5 here, you can, by choosing which variables to run t-tests on, you can double your false positive rate. You can see here the p for the column p is less than 0.05. The likelihood was 9.5% in these simulations. So the false positive rate was 9.5. In situation B, which was adding 10 observations to each cell if it was not significant, you can see here situation B, the addition of 10 more observations per cell for p less than 0.05, you can see this occurred 7.7% of the time. So you've almost increased your false positive rate by 50%. Yeah, and as you can see here, the likelihoods of generating a false positive gets worse and worse as you combine all the possible decisions you make about whether you test a dependent variable, whether you add data afterwards, or whether you add a covariate, or whether you drop conditions. If you do all four, you can see here if you look at just the p less than 0.05 situation, it's 60.7%. So you're more likely to find a false positive than to show that there is no effect. So this is problematic. The authors take a focus on sample size. So 70% of behavioral scientists admit to stopping data collection based on interim data analysis. So for example, you might want to, at the start of the study, collect 20 participants. And then you do an analysis of the 15 participants and find the p-value significant. So you decide to stop there and say, I only ever wanted to collect 15 participants anyway. So this is problematic. This is a questionable research practice. And we can see what the effects of doing something like that is over in this data. So in the figure, you can see on the y-axis percentage of false positive results. And the two lines indicate whether you start off with 10 observations per cell or 20 observations per cell. So a sample size of 10 or 20. as you can see here, the number of, on the x-axis, number of additional per condition observations before performing another t-test. So when it says 1, it means you just add one observation and you do the t-test again to see if it's significant. And you stop when you find it's not significant, when you find it is significant. So if you had 10 observations per cell and you run t-test after every single additional observation, you find a significant effect 22% of the time when there actually is not an effect. So that's problematic. We don't want that. It's lower if we conduct the t-tests at larger intervals. So if it's every 5 subjects, you only find a significant effect 17% of the time, 10 subjects 14.3% of the time, and 20 subjects 12.7% of the time if you had started with 10 subjects. So this is problematic. We want to reduce the rate that we find false positives. And a common misnomer among researchers is that if we find a significant effect at a lower sample size, it is necessarily going to be significant at a larger sample size. And this is not true. So testing after each additional observation can lead to false positives, and this is sometimes referred to as p-hacking. P-hacking your sample size to find a significant result. An example of this might be when your p-value is close to 0.05, so it might be 0.052 or described as trending towards significance. So you decide to add a few more participants in the hope that it will drop below that 0.05 threshold so you have a significant effect that you can write into your manuscript. But the problem is, statistical significance at a smaller sample size does not always mean significance at a larger sample size. And you can see this graph here, which illustrates that. It's the p-value plotted on the y-axis, and when the test is done, the analytical test is done based on the sample size. So it's not significant at the early stages when you have 11, 12, 13 participants, but you can see that the p-value can drop below this 0.05 significance level at 21, 22 participants, just for example, as an illustration. So if you were to stop your analysis then, you have a significant result, which is a false positive, because as you can see here, as the sample size gets larger, the effect or the p-value goes back above 0.05. So that is one particular practice that is problematic, that might be commonplace amongst researchers. So to prevent this kind of thing, the authors, Simmons et al., have some suggestions. The first one they say is determine data collection or a stopping rule before data collection begins. The second thing they suggest is collect at least 20 observations per cell. The third thing, authors must list all variables they collect in the study. This is all dependent variables and perhaps all manipulations of the independent variable. So authors must report all experimental conditions, including failed manipulations, so reporting how many levels your independent variable actually has. If observations are excluded, authors must also report what the statistical results are if those observations are included. And if an analysis includes a covariate, authors must report the statistical results of the analysis without the covariate. For those of you clued into open science and meta science, a lot of these things will remind you of pre-registration. So determining how many subjects or what your sample size is before the study begins and declaring that in a pre-registration before you run your data collection. And also listing what independent variables and dependent variables you are collecting, has become a new practice in scientific research to try and allay some of these problems with analytical flexibility. I personally am not a fan of the suggestion that collecting at least 20 observations per cell is enough. Based on the reason that I think 20 is an arbitrary number that they've selected here, I think the sample size should be justified based on maybe previous experiments or previous calculations of effect size. But other than that, these suggestions seem to be possible to implement if the field of science deems they're valuable, they're worthy. And in a good juxtaposition, the authors also point out some things that may pose as solutions but they believe are non-solutions. So the first one is correcting alpha levels, such as using Bonferroni to control post hoc family-wise error rate, so dividing your alpha by the number of tests you run, for example, so that your significance level is no longer 0.05. It's maybe, let's say if you run 2 contrasts post hoc, it will become 0.025. So those kind of controls don't control for the researcher degrees of freedom. They have no impact on, no adjustment for deciding how many subjects you ran or what test you run. So that's a bit of a problem. I also want to make a reference to a Larkin's paper called Justify Your Alpha. So perhaps we should be thinking about what is the appropriate alpha level in the first place. Bayesian statistics might appear to be a solution because you're collecting your evidence based on additional data, and you can make your conclusions based on the data alone. But the authors of the paper, Simmons et al., point out that this gives another set of analyses for researchers to include. So it increases the researcher degrees of freedom. They can choose to run a Bayesian analysis as well as a frequentist analysis. So it's just another additional set of analyses to run. And the priors that go into a Bayesian analysis also open up chances for researchers to make decisions. So that opens up more degrees of freedom for researchers to potentially find a false positive where there should not be one, where there should be no effect. Conceptual replications may seem on face value to be a solution to this, but if in the conceptual replications you select certain conditions, for example, if you had a low, medium, and high condition, but you only choose to replicate the low versus high condition, that could be problematic in terms of what results you find and what significant effects you find. So that is also another non-solution. And the last one, posting materials and data. And so the authors point out that they are supporters of people posting their data online and making it open and transparent. However, to prevent these issues occurring with researcher degrees of freedom and analytical flexibility, it requires work from reviewers to go through the data and go through the materials to double check that this has not happened and to see everything is in place. So these appear to be solutions, but and they in some way may be a little helpful, but they can also be non-solutions for this problem of analytical flexibility. I just want to highlight in our discussion from our journal club, we also discussed things like conferences where scientists will show, for example, in a talk or a poster, interim data and have run interim visualizations or conclusions about their data. So I thought that was a very interesting point. Should we consider doing something about how at scientific conferences people are analyzing interim data and showing off conclusions? Perhaps it's not a problem because scientists hopefully are good at saying this data is preliminary, and also that they have not yet completed data collection. So hopefully the scientists viewing that work do not take it for granted, take the conclusions for granted. So I thought that was another interesting point. And I want to also share that it seemed to be commonplace that amongst our group that someone had experienced some sort of questionable research practice at some point, or it was familiar to them. They'd seen it in a lab or had experienced themselves most likely mistakenly, these kind of practices. So it's important to think about how we will tackle these analytical flexibility, researcher degrees of freedom issues in the future. I hope you found that useful, and thanks.